So we're going to do some practice problems using linear equation. In this set of videos, we're going to focus on looking up linear interpolation. All right, so I'll give you a table. In this case, I give you temperatures at 5 degrees Celsius increments and the values of thermal expansion, the thermal expansion coefficient. Up here, you'll see that these values times 10 to the negative 4, and the units are 1 over Kelvin, or 1 over the temperature unit component, right? Don't worry so much about the units if those are new to you. What this is a demonstration of is how to find values of thermal expansion coefficient in between given values of temperature. Now, this does use the linear equation. It specifically looks at it from a perspective that you're applying the whatever 2 points that surround the temperature and the property you're interested in. You draw a linear line, right? So you apply y equals mx plus b onto it. Now, what we essentially are doing is identifying the slope between 2 points given to us on the table, and then saying that the slope of the point that we're interested in is in between, and we match that slope. So that's why I have this right here. Right? The assumption is that the slope is the same. Right? So m is the slope, is defined as rise over run, or a change in y over a change in x. And it probably makes a lot more sense in this form. So I often think about point 1 and point 2 as points on the table, and point 3 as the point that you're trying to solve for, right? It really doesn't matter what you define as your x parameter and what you define as your y parameter, as long as you're consistent from this side of the equation and this side of the equation. So a couple of rules is that you have to be consistent there. And in our case, we're going to be solving for y3. You could solve for x3. It's kind of completely up to you how you set it up, because it's a ratio. As long as these parameters are the same property as these parameters, just at different temperatures, then you'll be fine. And with a couple examples, you'll see that there's a very familiar pattern that will show up. But the main focus is when we look at linear interpolation, we are making the assumption that the linear equation can be applied between on 2 points that surround the value that you're interested in. But the main focus is the slope value. All right, so let's take a look at these examples. See if you can solve it. If you've done linear interpolation problems, pause this video and I'll walk through one way of solving these. All right, so let's say for the first one, 41 degrees. Where does that fall between? It falls between 40 and 45 degrees Celsius. So I'm going to use these values and these values. I'm going to define my temperature as my x and my thermal expansion as my y. The real variable that we use for thermal expansion all the time is alpha, so we'll see that in a second. So let's walk through this one. So on this left side, I have the rise in the numerator, y2 minus y1, right? So basically 4.2 minus 3.84, that's what's shown here. And I do want to keep the units and the magnitude correct. So times 10 to the negative 4, Kelvin to the negative 1, or 1 over Kelvin. So all of that divided by 45 minus 40, that's my x2 minus x1. 45 minus 40, and this will be equal to what I'm solving for, alpha, right? Alpha is the thermal expansion coefficient, minus y1, which is this thermal expansion, 3.84, divided by x3, which is the value I'm looking for, 41 degrees Celsius, minus 40 degrees Celsius. Now, if I want to switch this and I want to use what I'm looking for and 45 degrees and 4.2, that's fine. You'll see that that can be solved and you'll get the same solution. And so what am I looking for? I am looking for this alpha value. I know everything else, so I can isolate that value. And so if I rewrite this equation, I have alpha is equal to this ratio that I know, that's right here, times this temperature difference, 41 degrees minus 40 degrees, just move over there, plus the thermal expansion coefficient at 40 degrees Celsius. So just rearrange that. And you can calculate, you get a value. Now, a good way to check if you apply linear interpolation correctly is, if you did it correctly, you'll have two temperature values around the value you're looking for, which means the thermal expansion coefficient values must surround this value, right? So 3.912 is between 3.84 and 4.2, so we're in good shape, right? So you always want to double check. It is common to make mistakes on signs or have the properties swapped so you're not consistent, and it's typically, unless you have bad luck and you have coincidence where it's not when the values are pretty similar on both the x and y axes, very often you'll see that this value, if it's incorrect, falls outside the bounds of these two values, and that's a pretty good indication. Sometimes I'll even check this value, 41 degrees Celsius, is closer to 40 degrees than it is to 45 degrees. So I would expect this value, 3.912, to be closer to the corresponding 40 degree Celsius thermal expansion coefficient, 3.84, is than it would be to the higher end, 4.2. Right, so you can do your own checks. I'll go through the next two examples quicker, but it's the same concept, right? So 17 degrees Celsius, which properties would we want to look at? So 17 degrees Celsius is somewhere between 15 and 20 degrees Celsius. So I would use 1.51 and 2.07. So there's 20 and 15 degrees Celsius, the corresponding thermal expansion coefficients. And then similarly, we're solving for thermal expansion at 17 degrees Celsius. We rearrange and we could solve, we got 1.734 times 10 to the negative 4, and that's in between those two values. And finally, 92.5 degrees Celsius. This falls exactly in the middle of 90 and 95 degrees. And so when we solve this, we'll use 6.66 and 6.87. And if you recognize that your fall right between, you don't need to go through all this math. You'll see that it will fall exactly in between. So you can take basically the average of these two parameters, but the same process can be solved to identify what the thermal expansion alpha at 92.5 degrees Celsius. All right, so this gets used a lot. Sometimes you do it by hand. A lot of times you'll be writing code and you want a computer program to pull these values for you. So you can see there's real important applications for using linear interpolation in linear equations. So we'll do a couple more examples. I'll go through it a lot quicker. We'll use the same general concept.